So welcome back to another topic. Today our big idea are Riemann sums and definite integrals. So integrals is definitely one of the big words you want to learn in calculus. It's one of the most important things. As you can see, we have quite a few keywords today. We've kind of got an abundance of them. So that's the bad news. We're in for a pretty long video today. The good news is there isn't a video for tomorrow. What we're going to do in class is we're going to spend today talking about these ideas, working on them tomorrow, working on them again. I just think it's better to get you sort of all the ideas up front so then we can play around with them a bit in class. Alright, let's do this. Okay, so we just built this machine for finding area. We said grab yourself a function, put it in this machine that takes sums and limits, and it's going to pop out for you area. And you know, mathematicians have been thinking about this for a while, but this guy came around named Bernhard Riemann. And Riemann was looking at this thing, this limits and sums, and he thought, well, what happens if I do something different with this function? So Riemann thought, what if I use a function f that is not always positive in here? So if we look at this function, if we look just from 0 to 2, it's positive. We could totally use this formula, run through the calculations to figure out the area of this region here. But what happens if we go all the way from 0 to 4? We got this negative space over here. Well, what's going to happen? Now, Riemann also had a couple other crazy ideas. He also said, besides just using any function, let's go ahead and not break this up into nice intervals that are always the same size. Let's break them up into all kinds of different pieces. And then let's just go ahead and use any number we want to build our rectangles here. Let's use some of them are lefts, some of them are rights. Doesn't matter, some of them go through the middle. We just go all willy-nilly there. So we're doing all over crazy rectangles of all different sizes. What's going to happen? So this Riemann guy was so crazy that he ended up with having this whole thing named after him. They're what we call today Riemann sums. So what a Riemann sum says that you take any function, as long as it's defined on the closed interval, doesn't have to be positive or negative, I don't care, just pick yourself a nice function, and let delta be a partition of AB. Basically what you're going to do is these are going to be the points that define the edges of your rectangles, and you give them each their own width. And then if you pick any point in between those points to build your rectangles like we did above, add those all up, so add up the area of just some sort of almost random collection of rectangles as you go. This is going to be called a Riemann sum. And what he found out with these was something pretty cool. He figured out this huge box of stuff. Now, the whole thing it's important historically, but it's not important for what you need to know, okay? But let's read it anyways. It says if you've got your function defined in a closed interval AB, and the limit of a Riemann sum over the partition exists, we'll talk about this, then we're going to say that this function is integrable. So if you run through this computation and you get a number out, equals a number, not plus or minus infinity, then we're going to say it's integrable. And what we're going to do is we're going to use a special set of symbols here to denote this thing, and we're going to call this the definite integral. So what the definite integral means is it means run through one of these sums. Now we're not crazy, okay? Riemann said you can use any sum you want, so we're going to use one that we know. We're going to use our traditional right sum that we've been using all along, okay? No new sum. When you see these symbols here, when you see this set of symbols here, it just means calculate the right sum with the limits and everything. That's all it means. And we're going to give this thing a special name. It's going to be called the definite integral of f from a to b. The number a is going to be called the lower limit of integration, and b will be called the upper limit of integration. So every time you see these symbols from now on, just think to yourself, oh, well, I got to compute that right sum. That's what I got to do, and I'm going to get myself a number. Now let's take a little bit and chat about how we are going to move from the set of symbols we had on the right that we're okay with to the set of symbols that we have on the left. So the first thing to note is this fancy looking S-type symbol. And so this thing is called the integral symbol. And what it does is it looks like a fancy S because it stands for sum, just like we had a sigma that stood for sum. So this really is representing the idea that we're going to be adding something together. The next interesting looking symbol is the differential, which is denoted by dx here. And this takes the place of our delta x over here. So dx, the differential, represents a small change in the value x. just like delta x represented the smaller and smaller widths of our rectangle here as we increased n. Now these are very important distinctions in higher mathematics and later, and also if you take Calc 2. But for now what you want to do is you want to think of delta x as sort of used when you measure it. It really does represent a change in x, or the width, whereas dx is used more of an abstract representation of it. And it's sort of stylistic, but it really indicates to you the variable being used. Another thing to note is that it doesn't really matter what we use. We can say the integral from a to b of f of t dt. This is the same as the integral from a to b of f of u du. Any letter you want to use there, it just tells you basically that your variable is going to be u in this case, or whatever it happens to be. And the last thing to note is that a and b are where you start and stop respectively, so they'll tell you what you feed into the delta x term to get your b minus a over n. They're just going to be your endpoints. A couple more notes before we take this definite integral out for a try. The first is a warning. The definite integral is a number, okay? If you're doing it right, you should get a number when you're all said and done. If you don't get a number, if you get something like a function with some variables and stuff in it, something's gone wrong, okay? It should really be a number. Another thing to note is that continuous functions shouldn't give you any troubles. If you have a function, it's nice and continuous on the closed interval, then the function is going to be integrable, that is, this thing exists, and this thing will equal, once again, a nice number. It's not going to be infinity or anything crazy. You're not going to get it does not exist. It might take some work, but you can totally figure it out. Alright, so let's go ahead and try this thing. Let's evaluate the definite integral from 0 to 4 of the function negative x plus 2 dx. So the thing to remember here is that this means we need to compute our limit definition. We need to compute our right sum. So the first thing we want to do is set some things up. So first we compute our delta x, and we can figure out delta x based on the fact that we have a 4 as our upper bound here in this case, and we have a 0 as our lower bound. And what this means is that our a is 0, and therefore we start at 0. And we figured out our delta x before. So now we've got both our width of our rectangles and the point we're going to use. So now we can run through our old machine here. So according to our definition, all we have to do to figure out this definite integral here is to run through all the computations here for our machine. So these steps I'm going to go through them kind of quick, but it's the same steps as we always have to do. So of course our first step here is we take the 4 over n and we factor it out. And next we'll want to break up this sum and roll through with our definitions there of how to compute those. And obviously here we would say that I skipped a step. That's what I did there. But all I've done is I've broken up and computed the sum from 2, which gets me the 2n. And here I factor out the negative 4 over n, and I note that I in the sum will give me the n times n plus 1 over 2. And so now I'm left with just a nice limit to compute. So next, of course, I need to multiply everything out. And after doing this algebra, what I need to do, of course, now is to compute the limit. And here's where something interesting happens, okay? So when I compute this limit, if we look here, well, I've got an n squared over n squared. So this means in the limit, I just need to look at the first coefficient. So I get a negative 16 over 2. Here I've got an n over n squared. So this term isn't going to matter because this is going to go off to 0. And last, I have just an 8 on the end. So I just need to add 8 to what I get here. Well, let's see. Negative 16 divided by 2 is negative 8. Plus 8 is 0. So this is interesting because I got 0. Now if this was an area, then I should have gotten a positive number. I can't have area 0. So we want to look at the graph here and try to think, well, what happened? So whatever this integral thing is measuring, I start measuring it here at 0, and I stop measuring it here over at 4. So one of the ways to think about this is to think about physically, if this graph had a real representation in the world, what would it mean? So let's suppose I'm a person traveling with velocity, given by v of x is equal to negative x plus 2 miles per second from time 0 seconds to time 4 seconds. So we're going to give this thing some units and some meaning. So one thing we can ask is, well, how fast are you moving when x equals 0? In this case, we put 0 into my function, and I get negative 0 plus 2 is 2 miles per second. Okay, because we always want to be careful with our units here. And so what I could do is I could go up to my function in here and think, well, this thing is just calculating areas, really, or it's calculating rectangles at least. So what happens if I followed this along for 1 second here? Well, this would mean in my area calculation that I was traveling 2 miles per second times 1 second. And note the units here, the seconds cancel, so this would mean that I was able to travel 2 miles. I'm moving pretty quick, 2 miles a second. It's a good pace. And so this is interesting because this is what area here really represents, is the number of miles you're traveling. Another thing I could ask is, what is the definite integral from 0 to 2 of negative x plus 2 dx? And we could go through our whole limit definition here, but what we saw before is really we're trying to calculate, since this is a positive function, just the area up here. We're just trying to calculate the area in this triangle, and well, let's see, this triangle is going to be 2 units tall times 2 units wide times 1/2 since it's a triangle, so we end up getting 1 mile total. So what we could do is we can graph this idea. At time 0, we can say we start at position 0, and then at time 2, we've gone 1 mile total. So this is what the graph of our function looks like if we only calculate these 2 points. And we could also calculate some points in between for some approximations, and we could fill in the shape of our graph a little bit. Now let's look what happens over on the right side of our graph. On the right side, what happens is we were moving along at 2 miles an hour, but it appears that we're slowing down. We slowed down to 1, and finally, here at time 2, we're going 0 miles per hour, miles per second rather, and now we've reversed our direction. Now we're moving in a negative direction. And so what this integral is trying to tell us is it's trying to tell us about the total change in our position. It says you sure were increasing your position over here until time 2, but then you started moving negatively, and so what happened is you moved in the reverse direction. And so in total, this 0 means you've moved 0 miles net overall. That means while you did travel a mile out and back, overall you're exactly where you started with. So here's a very important idea, is that integrals measure total change, okay? So this integral of this function, if it's velocity, it's not measuring the total distance a person's moved, it's measuring total change. So even though this person has gone out a mile and come back, overall, net, they're back where they started. So this is super, super important. Write this down like 5 times in your notebook, please. Integrals measure total change. So one last note before we go. We saw that this integral here, from 0 to 2 of negative x plus 2, geometrically gave us 1 mile. And we found that by figuring out the area of this triangle. So what do you think that means about the area of this triangle over here? That is, this triangle over here is going to be the integral from 2 to 4 of this function. Take a guess at what you think the value of that integral is going to be. And now we'll figure out ways to figure that out pretty nicely. So while everyone, I'm sure, is loving the limit definition, working through limits and sums, there are some nice ways and shortcuts we can use in order to help us compute limits a little bit faster to make better use of our time. So the first thing we have are these 2 special definite integrals. The first one says that if f is a function defined at a point x equals a, then we can define the integral from a to a of f of x dx equal to 0. The way I like to think about this first one is how much can you change by standing still. Also, in this case, the width of any particular rectangle is going to be a minus a over n is going to be 0. So if you have a bunch of rectangles that don't have any width, of course, when you add them all up, you're going to get 0. Property 2 says if that f is integrable on the interval a to b, then we can define the integral, so careful here, the integral from b to a as the negative, the opposite of the integral from a to b. So the way I think about property 2 is that walking backwards reverses any and all progress you've made. And this also occurs because now delta x is going to be a minus b over n, which is the negation of b minus a over n. It's the opposite. So whatever your total area was before, this is going to be the opposite area. So suppose someone comes up to you and tries to trick you and says, what's the integral from 4 to 0 of x dx? Okay, this someone's probably me, and it's probably not coming up to you. It's more like a quiz or an exam or a homework problem. All you got to do is say to them, well, let's think about this. If I'm going from 4 to 0, that's just the opposite of going from 0 to 4 of x dx. And now I could run through this limit definition here if I really wanted to. But instead, I'm smart enough that I'm going to look at the graph. And that is a nice looking graph. If we look at this graph here, it's not too hard to tell that the base, if we go from 0 to 4, is a nice triangle, length 4. The height is 4, so this means my integral is going to be negative 1/2 4 times 4. So if I do my arithmetic right, this is hopefully going to be negative 8. So this is all my integral is. It's just the opposite of the positive version of my integral. No muss, no fuss. Also, probably put right here something to indicate that we've done it geometrically, and we might want to draw a picture as well so everyone can be happy that there's enough work shown that we all know what we're doing. So the next useful property we have is a theorem called the additive property of integrals. And it says that if a function is integrable, that is if its integral exists on this interval a to b, and we pick some point c in between a and b, then in order to calculate our single integral there that we want, what we can do is we can calculate these two integrals instead on the left. So let's look at a good graphical example of this. So suppose we need to compute the integral from -1 to 1 of the absolute value of x dx. Well, in this case, we could go ahead and apply our limit definition, write out all that limits and integrals and some stuff, but we don't want to do that. Instead, what we want to do is we want to use our theorem. And our theorem says that we can break up integrals at points in between. So if we look graphically what we have, over here, -1 is going to be our a value, and 1 is going to be our b value, and we want to compute the integral in between. So what this is telling us is what we really are interested in is computing these regions and adding them together. And so overall it's not a single shape, but what we can do is we can break it up here at 0 into two separate integrals to compute. So our theorem tells us that what we can do is we can write this single integral as two separate integrals. One from -1 to 0 of the absolute value of x dx, plus the integral from 0 to 1 of the absolute value of x dx. And what we can do here is, again, we can do two different things. One, we could go ahead and compute the sums for each of these, because these integrals are pretty nice now. This is going to be -1 to 0 of the opposite of x dx, because the absolute value, since it's negative, we negate it, plus the integral from 0 to 1 of x dx. And we could use our limit definition, but instead what I'm going to do is I'm going to compute these things geometrically instead. So geometrically, if we look at our first integral here, well, this is going to be the area of a triangle, and the triangle formula gives us this is going to be 1/2 times the height, which is 1, times the base, which is 1. Plus, geometrically, we can compute our second integral from 0 to 1, which is again a triangle, and this triangle is 1/2 times 1 times 1, its height times its base. And so when we compute this thing, altogether what we end up with is a total integral of 1. And what's really nice is this avoided the limit definition because it was pretty geometric, and it worked because we can identify geometrically what these shapes are. Now you can also do this anytime you want. You can pick any point in between. We could have, if we really wanted to, we could have computed the integral from -1 to 1/2, the absolute value of x dx, plus the integral from 1/2 to 1 of the absolute value of x dx. The problem is is that this doesn't give us nice geometric shapes to compute. So instead it would have said, well, compute this area, which is a trapezoid, and then you still have the problem that you have two triangles there to compute. So the choice is always up to you of where to break these things up, but you want to try and break them up at good points. So now it's another time to look at what are called the linear properties of definite integrals. So suppose you have two integrable functions f and g on an interval a to b. K is a constant, just some nice real number. Then the functions k times f and f plus or minus g are both going to be integrable. And in fact, we have two nice properties. The first one says that you can take the constant and move it outside the integral. The other one says that if you have plus or minus inside an integral, that becomes plus or minus of two separate integrals. Now, we've seen these a lot. We saw them with limits. We saw that the limit, as x approaches c, of k times f of x is simply k times the limit as x approaches c of f of x. And similarly, we've also seen the property that if you take a summation from k equals 1 to n of a sub k plus b sub k, what you can do is you can write this as two separate sums. These properties occur all the time. Anytime you see them, they're called linear. So it means we've got these things for limits, we have these properties for sums, and because our integral is just a fancy way to write these sums and limits together, that is, if we had the integral from a to b of k f of x dx, well, what does this mean? This means the limit as n approaches infinity for the sum from I equals 1 to n of k times f of xi times delta x. Well, what happens? This k slips out of the sum. It also slips out of the limit. So overall, we just have k times the integral as we've desired. And so these properties occur over and over again and are of great help when computing integrals. So let's see an example of how we can use these. So let's go ahead and use these linear properties to find the following integral using the fact that we know three certain integrals already. The biggest idea is you just break it up into easy pieces, okay? We always want to break a complicated problem down into some simpler problems. So if we look at this, well, what we can do is we can use the fact that right here we're subtracting and here we're adding to break our integral into three separate integrals. So this means this original integral is going to be equal to the integral from 1 to 3 of x squared dx minus the integral from 1 to 3 of 4x dx plus the integral from 1 to 3 of 3 dx. So this is all using property 2 that we can break up our integrals because we're adding and subtracting. Now this is good because this first piece matches exactly a number we already know how to compute, and similarly the last piece here matches exactly something we already know. So these are just numbers already and we know what those numbers are. The last thing to do is to get our middle piece here to look some more like this. They're not quite the same yet. But what we can see is we can see that we have a constant out here, the 4, and we can move that 4 out front. So what we end up with instead is we end up with now an integral we know minus 4 times an integral that we also know, plus finally an integral that we know. And so now we're left to simply substitute and compute. We know this is 26 thirds minus 4 times 4 plus 6. And what we simply want to do then is go ahead and add all these things together, and if we do our arithmetic correctly, we'll get negative 1 and 1/3. Now I encourage you, if you're bored and you can't sleep tonight, to try working through the original integral using the limit definition. It's not difficult, but it turns quickly into an algebraic mess. So always breaking it up into smaller pieces is nice. It's also easier, if you had to on your own, compute each one of these integrals because they're a lot simpler to compute than computing the whole thing. Algebraically, it's just a lot less work to compute them separately. Okay, so that's it for this lesson. I know it got a bit long, but remember that this stuff we're going to go over in class tomorrow, so make sure you try the problems posted on Blackboard and post a question. And we're going to go over them for 2 days in class, so we're going to have plenty of time to go through lots more examples in class. working with your group to get a lot of your homework finished off. But as always, if you have any questions, make sure you post at least one to Blackboard. Otherwise, let me know. Thanks.